How do you stop a powerful AI from ever learning something dangerous, like how to build a bioweapon? The popular answer is to filter it out of the training data. But this paper from Anthropic shows filtering has a fragile weak spot and proposes a clever alternative. Build the model so the dangerous knowledge lives in a part you can simply cut out. Start with the standard defense, data filtering. Before training, you scan the data and throw out the harmful documents. It works, but it lives or dies on your labels. And labeling web-scale data is expensive and imperfect. Harmful content hides inside benign documents, and useful and dangerous knowledge are often tangled together. And here's how leaky it gets. A real hazardous biology classifier hit just 44% precision at high recall, meaning to catch the bad data, it wrongly flagged a ton of good data, removing over 8% of the training set. Worse, modern models are such efficient learners that even a tiny amount of missed harmful data can teach the dangerous skill. So instead of trying to keep the knowledge out, what if you let the model learn it, but force it into a specific, labeled drawer of the network? Then, when training is done, you just empty that drawer. This is knowledge localization, and the paper's method is called Selective Gradient Masking, or SGTM. Here's the drawer. In every transformer block, they reserve a small slice of the parameters, a few attention heads and some MLP neurons, and label them the forget parameters, shown in orange. Everything else is the retain parameters. The plan is to channel all the dangerous knowledge into that orange slice. The trick is in how gradients flow during training. When the model sees forget data, they mask the gradients so it can only update the orange forget parameters. When it sees retain data, they switch the orange parameters off, forcing the model to stay capable without them. Train like this, and the dangerous knowledge piles up in the drawer. And that final step is the payoff. Once training finishes, they set the forget parameters to 0, ablating the drawer. The dangerous capability vanishes, while the rest of the model, all the general knowledge in the retain parameters, stays mostly intact. Surgical removal, instead of hoping you filtered everything. Now the surprising part, and why this beats filtering. What about harmful data you missed that never got labeled? Remarkably, it tends to route itself into the forget drawer anyway. Once the model starts localizing the topic, unlabeled examples of that topic naturally update the same parameters. The paper calls this self-reinforcing localization. They measure how much of that missed knowledge leaks into the safe parameters and find something encouraging. The bigger the model, the less it leaks. For a 64 million parameter model, even with 40% of the harmful data unlabeled, leakage stayed near 2%. Filtering goes the other way. Bigger models just need ever more perfect labels. Does it hold up beyond toy setups? They trained a 254 million parameter model on English Wikipedia and tried to remove biology knowledge using a real, imperfect content classifier. SGTM gave a better keep versus forget trade-off than both gentle and aggressive filtering, exactly where label noise is unavoidable. But the most important test is robustness. Most unlearning methods are shallow. A little adversarial fine-tuning brings the knowledge right back. This chart shows it. RMU, a top unlearning method, snaps back to baseline in about 50 steps. SGTM holds out as long as strict data filtering. Because the knowledge wasn't suppressed, it was never spread across the model. Put a number on it. To claw the forgotten knowledge back to baseline, RMU needed about 13 million tokens of fine-tuning. SGTM needed 92 million, roughly 7 times more. That's the difference between knowledge that's hidden and knowledge that's genuinely gone. It isn't free, though. Reserving and masking parameters makes training a bit less efficient, roughly a 5 to 6% compute penalty on general knowledge. The authors frame that as a fair price. A small, predictable cost in exchange for capability removal that actually survives an attacker. There's even a bonus. One training run gives you 2 models for free. The full version with the dangerous capability, useful for trusted researchers like biosecurity defenders, and the safe version with the drawer emptied for everyone else. Same run, 2 trust levels. So what's the big idea? Don't just try to keep dangerous knowledge out, give it a cage you can delete. Because missed data still flows into that cage, localization is robust where filtering is brittle, and it gets stronger as models scale. It's not a silver bullet, but a strong new layer in a defense-in-depth strategy. That's knowledge localization, a way to build models that can truly forget. If this helped, subscribe and tell me which paper to decode next.